And now we're talking about convolution and Laplace transforms. And this property will allow us to solve integral equations, differential integral equations, and equations involving integrals instead of derivatives or even including derivatives. Anyway, this is the definition of a convolution. And we use this star as the operator. F convoluted with G means put them into this integral. These are for when these functions are 0 for argument less than 0. It's this integrated over tau. And by a change of variable, you could show that it's commutative. F convoluted with G is equal to G convoluted with F. Now let's say we just simply multiply Laplace transforms. We'll see where this is going. It means we multiply these two things. That's the Laplace transform, that's the Laplace transform. I'm using tau and beta here instead of t, because I'm going to put them together. I want to distinguish them. When I multiply integrals, I can make it a double integral. And then by a variable substitution, I'll say t is tau plus beta. And I end up with this new integrand with some new limits. And I'm not going to go through this explicitly. You ought to see a diagram. You're not super slick with double integrals. But from there to there, this is what you have, and you recognize this part as the convolution of f and g. Well, the whole thing then is the Laplace transform of the convolution. So we have a Laplace transform pair. Laplace transform of a convolution in the time domain, I just multiply the Laplace transforms in the Laplace domain. So here's the new property. Convolution in the time domain is multiplication in the Laplace domain. And what if the g function, or one of those two functions, is just the constant 1 or the unit step? Then this convolution just becomes a normal integral, 0 to t, of whatever your function is. Which means the Laplace transform of an integral is the Laplace transform of the function convoluted with 1, which by this property is just the Laplace transform of the function f divided by s, which makes some sense if you remember derivatives. When I took a derivative, I had to multiply by s. I took the derivative of the time function, I multiplied by s in the Laplace domain and subtracted off some initial condition. When I integrate, I divide by s, and it makes sense. So this is something you could put in a table as well as this property. The integral of a time function is dividing by s in the Laplace domain. Let's do some examples. Let's find the Laplace transform of this thing and then evaluate that integral. Well, let's see. This thing up here is the convolution of sine and cosine. Be careful, it's not the convolution of sine and cosine of t minus tau or something. It's just a good old convolution of sine t, cosine t. I'm integrating the tau out of it when I do the convolution. And that convolution is just multiplying the Laplace transforms. And I could look these guys up on the table, multiply them together, there's what I get. So this is the Laplace transform of this. Now let's evaluate this. Well, let's see. I evaluated, one way to evaluate it, rather than taking this integral is to inverse Laplace transform this guy well, that's it, inverse Laplace transform this guy. So this isn't quite in the table directly. Yeah, this isn't in the table directly, but this is 2s over this, at least in the table I use. So I just multiply by a half to make it come out right. So it's a half, and this is in the table. If it weren't, you might have trouble. But if you just inverse the Laplace transform of the convolution, and that's what the convolution is. So instead of you having to evaluate this integral, you could find its Laplace transform and then invert the Laplace transform. Let's see. The Laplace transform of this guy. Well, this is an integral of something that's in the table, t sine tau. You don't see a t minus tau here, so this isn't a convolution of t and sine. It's a convolution of t sine t and 1, but that's just 1 over s, the Laplace transform is 1 over s, the Laplace transform of what's in here, t sine t. And in the table I used, this is in the table, it's 2s over s. We're using the same property of the table. And when I divide by s, I get this. If I had to evaluate what this integral is, I could take the inverse Laplace transform of this. And we'll assume that that's in the table. It's like this. This is the inverse Laplace transform of that. If you can do that, you wouldn't have to take this. It's going to be kind of a long lesson, but I'll try to get it all out of the way. Let's say you have, now we're doing a differential equation, actually a integral equation. Solve this equation here. You don't see any derivatives in it, but you do see an integral. Recognize this is a convolution. Here's a function that's just got tau, and here's a function of t minus tau. So this thing on the right is the convolution of e to the t minus e to the minus t convoluted with the function f. And this is just f of t. Should probably put that on there. So now like before, I take the Laplace transform of every term, term by term. Laplace transform of t is 1 over s squared. Laplace transform of little f, we'll just call it big F, whatever that is. Laplace transform of the convolution is a multiple of the Laplace transforms. So e to the t is 1 over s minus 1, e to the minus t is 1 over s plus 1. Laplace transform of little f is whatever big F is. Now I can get all the big F on one side. Well, actually, not quite yet. First, simplify this thing a little bit. And it's just 2 over s squared minus 1 times f. Now I can get all the f stuff on the same side. I'll have a 1 over s squared on the left. This part on the right plus that 2, that all over the same. Simplify it or get it in one quotient. And I can now solve for this f. This f equals s squared minus 1 over s squared, well, 2s to the 4th. Yes. So we write it, and now I can find things in the table. 1 over s squared and this 3 factorial over s 4th. Those are in the table. There we go. This is the solution to that integral equation. Here's another one. subsidiary equation. Take the Laplace transform term by term. So this will be a big F. This is just the integral of F. So in the Laplace domain, it's divide by S times big F. Laplace transform of 1 is 1 over S. Algebraically solve for F. I get F equals 1 over S plus 1. Look that up in the table. F equals e to the minus 2. This is the solution to that integral equation. Integro-differential equation. I've got a differential here and an integral here. And since I have a first derivative here, I'm going to need an initial condition. So again, take Laplace transforms term by term. S times big Y. This is 1 over S. This is 1 over S squared plus 1. This is just the integral of Y. So it's big Y divided by S. There's our subsidiary equation. Algebraically simplified to find S or find Y in terms of S. We'll go through that algebra. So Y equals this mess over here. These things are in the table. Go. Here's the solution. This integro-differential. We're using the same method. Now we have a new property for convolutions and integrals. All right. One more lesson on Laplace transforms.